They seem to defy gravity. Forged from concrete and steel, skyscrapers loom over today's urban jungle. They embody the souls of those who built them, the strength and courage of high steel workers, but also the danger of such a passion. For as gracefully as they rise, skyscrapers collapse with unparalleled devastation. Yet in the face of potential disaster, architects continue to design these superstructures higher and higher. It's become a race towards the heavens to lay claim to the title, tallest building in the world. How far and how high will this never-ending race take us? And what engineering marvels keep these superstructures standing? In Nagoya, Japan, despite continual rainstorms, work progresses on one of the world's largest skyscrapers. The JR Central Towers, still in its infancy, is being built in the middle of a crowded city and on top of a busy train station. Every facet of modern engineering skill is daily put to the test. When completed, this enormous skyscraper will encompass over 4.5 million square feet.
It's about the size of the Pentagon, or larger than one tower of the World Trade Towers, the Twin Towers, and one of the largest buildings in Japan, if not the world.
Engineers in Nagoya, like many throughout Japan, have no choice but to build up. Land is scarce, and real estate prices are soaring. To meet the needs of a growing population, skyscrapers are the only answer. In the capital of Malaysia, space isn't an issue. Land for construction abounds. Yet in Kuala Lumpur, a modern 1,400-foot skyscraper is being built. The Petronas Towers are an amazing structure of glass and steel. With 88 floors and 100-foot spires, these twin towers are a monument to architect Cesar Pali's dreams. Whether built out of need or inspiration, constructing these mammoth skyscrapers relies heavily upon technological advances. But modern science isn't perfect, and tragedy follows when one comes tumbling down. Unwavering before such catastrophes, engineers continue to build bigger and taller superstructures.
Well, I think man has always wanted to get higher and higher. He always climbed the mountain to see beyond. It's also getting up to be taller, to overlook everyone else, or to be recognized, or to feel more powerful.
To build these modern-day monoliths, architects and engineers first had to conquer the force of gravity. During the mid-1800s, the only means of vertical transportation, other than climbing stairs, was a rope and pulley system driven by a steam engine. However, the system was too dangerous for passengers since the ropes often broke. Frustrated, Elisha Otis invented a safety brake that locks the platform to its guides. In 1852, what seems a minor invention paves the way for the modern elevator. Slowly, the public begins to trust the Otis elevator. Upper-level floors become fashionable and profitable as architects quickly adopt this new means of vertical transportation. Even with the use of an elevator, buildings rising above 200 feet remain a dream. The building materials of the day, bricks, stones, and mortar, are simply too heavy to allow great heights. But in 1885, with the invention of the steel cage structure, the modern skyscraper is born.
Rather than build up from the ground, they built a cage inside, your bone structure, your person, the skeleton, and then they put the skin on the outside. And then the weight of that material is held at each floor level rather than passed all the way down 5, 10, 20, 30 stories down to the ground and held at the bottom floor. No, it's all hung off of this very strong structural cage, which is much lighter now because it's out of steel.
Because the steel structure bears the majority of the weight, the exterior, or skin of the building, can now be made of much lighter materials, such as glass and aluminum. The result is an explosion of buildings taller than anyone has ever seen.
The limits on masonry buildings were about 200 to 250 feet, which is equivalent to about 20 stories. With the advent of the separation of the two systems, the skeleton from the skin, we became capable of pushing higher and much higher, up to 50, 70, 80, or the Empire State Building type, up to 100.
For over 100 years, the steel cage structure has enabled engineers to build skyscrapers higher and higher. It's the backbone of every tall building's design, even the 800-foot JR Central Towers in Nagoya. The skyscraper is made up of 3 steel cages. One forms the base of the building, while 2 rise up within each tower. Without this technology, skyscrapers rising above 20 stories wouldn't be possible.
In Malaysia, over 26,000 tons of steel and 160,000 cubic meters of concrete have been used in the framing of the Twin Towers. These 88-story steel and concrete skeletons will help the Petronas Towers claim the title, tallest building in the world. Higher and higher they rise. But at what altitude do skyscrapers become too dangerous? Over 50 years ago, a deadly incident magnified these risks. In 1945, the tallest building in the world is New York's Empire State Building, rising an incredible 1,250 feet. Built in just over 13 months, its claim as the tallest skyscraper will last nearly 40 years. Perhaps this building's greatest achievement is not its long stay at the top, but its jarring reminder of the dangers of building so high.
The Empire State Building and all New York City were wrapped in fog as a B-25 Mitchell bomber trying to reach a nearby airport crashed into the tallest structure in the world.
Although the pilot and 13 others died, the building sustained little damage and was open for business 2 days later. Its ability to survive a collision with a World War II bomber seemed to validate modern engineering technology. Soon, a skyscraper building boom swept across the United States. "29 years later, the Sears Tower is built 1,454 feet above Chicago, becoming the tallest skyscraper in the world. While skyscraper construction within the United States has steadily declined since the early 1970s, the JR Central Towers and the Petronas Towers are at the forefront of a building boom along the Pacific Rim. The competition is as fierce as ever.
You built a skyscraper, they're taller and taller. Some of them make absolutely no economic sense, but they're being built nonetheless. It's just amazing the number of projects that are being done out there. They're being done strictly for ego. There's no other reason. And there's no economic reason for them to be built other than sheer ego.
As this construction craze of enormous skyscrapers spreads throughout the Pacific Rim, the engineering world is once again thrown into a battle to become the world's tallest building. The Petronas Towers are planned to top off at 1,476 feet, 22 feet taller than the Sears Tower. Only time will tell if this architectural pursuit will prove deadly. In New York, to avoid future collisions, airplanes were simply rerouted. But the engineers of the JR Central Towers and the Petronas Towers are threatened by unavoidable forces. They're building skyscrapers in one of the most seismic active regions in the world, where the threat of a major earthquake is constant. Relying on the innovative designs that enabled the Sears Tower and the Empire State Building to reach such monumental heights won't help. They weren't designed with earthquakes in mind. How safe will these new structures be when a violent earthquake shakes their very foundations? As construction continues on the JR Central Towers, the Petronas Towers nears completion. Engineers of both buildings hope their state-of-the-art technology will pass the test. If it fails, these latest additions to the tallest buildings in the world could come tumbling down. Modern building design will be pushed to its limits when Mother Nature strikes. The construction of the JR Central Towers is a collaboration of the top engineering minds in both Japan and the United States. It's also one of the most hazardous projects in the world. Located directly below the site is Nagoya Station. 1.5 million people pass through here each day, disregarding the huge skyscraper being built above them. But what would happen if an earthquake hit such a densely populated area? It's happened before. September 19th, 1985. A killer earthquake registering 8.0 on the Richter scale rocks Mexico City.
Sigue temblando un poquitito, pero pues vamos a tomarlo con una gran tranquilidad. Vamos a esperar un segundo para poder hablar.
More than 10,000 people are killed. And over 100,000 are left homeless as the quake damages nearly 3,000 structures. 400 totally collapse. And for the city's towering skyscrapers, once a symbol of modern Mexico, this is the most devastating quake ever.
The ground was actually moving back and forth for a minute and a half or so, about like this. It just sort of a gentle motion back and forth. And certainly most buildings, if you were in them, you'd get a little seasick, but you wouldn't feel very much. It's not a very violent motion unless you happen to be a tall building.
During the 90 seconds of shaking in Mexico City, some skyscrapers swayed 6 feet, 3 times farther than what is considered safe. Neighboring buildings slammed into each other, causing major damage. 10 years later, a small office in the Japanese city of Kobe is tossed upside down. Just one of the many casualties in a town devastated by a 7.2 earthquake. Over 100,000 buildings are destroyed. Another 80,000 are severely damaged. And in downtown Kobe, home to most of the city's skyscrapers, 60% of the buildings sustain significant structural damage. Over 20% are completely destroyed. It's in this seismic environment the latest skyscraper building boom has erupted. Whether guided by sheer need or pure ego, architects are designing some of the tallest buildings in the world on some of the most unstable land. But the devastating failures in both Mexico City and Kobe have provided the building community with valuable insights. When the Earth moves beneath these monoliths, the skyscraper's center of gravity becomes offset. The top of the building tends to lag behind the base, putting more stress on the columns.
At the very least, the building could end up with a permanent bend in it, which would yield it an economic total loss, although the occupants may survive the situation. The worst case would be that it got so far out of vertical that it actually fell over, and that, of course, would be a catastrophic situation.
Using computers to simulate the shaking a building sustains during a major earthquake, researchers discovered that strengthening a skyscraper's foundation may prevent these structural failures. In Nagoya, Japan, only 140 miles from Kobe, the engineers of the JR Central Towers are putting this latest research to the test. 4 stories below the proposed lobby, a vast digging campaign is underway. In this subterranean cavern, architect Paul Katz hopes to build the strongest foundation ever constructed for a skyscraper. To anchor the building to the foundation, engineers drive 125-foot-high steel beams 60 feet into the bedrock. Eventually, these columns will be encased in steel reinforcement bars and concrete. This will become the base frame of the building and bear the majority of its weight.
You can see here the tremendous amount of reinforcement that is needed not only to carry the weight of the building, but this is where all the forces of the building come down, and in earthquakes this is the part of the building that resists the lateral shaking that an earthquake will affect on a huge structure like this.
As an added precaution, engineers will then fill the entire cavern with over 1.5 million cubic feet of concrete, creating what is called a mat slab foundation.
Is what we're seeing in the excavation here is entirely going to be filled with concrete, 5.5 meters in height, which in a way the whole building then floats on and helps support the building from tilting and unifies the entire building.
For a mat slab foundation to work, steel piles must be anchored in solid bedrock. Once in place, they're locked together into a stronger structure by the cement slab poured around them. Finally, the steel structure of the skyscraper above ground is bolted to the foundation piles below. This becomes the skyscraper's skeleton, a single rigid structure anchored by a cement slab able to absorb most of an earthquake's lateral force. The mat slab foundation prevents the steel cage structure above ground from swaying too far during an earthquake. The taller the building, the larger the foundation necessary. Because of the limited space surrounding the skyscraper, the JR Central Towers foundation is forced to be excavated in an underground cavern, while the Petronas Towers foundation will spread out, covering over 1.5 acres. The building that will become the tallest skyscraper in the world requires one of the largest mat slab foundations ever constructed. Before a drop of concrete is poured, the bedrock at the proposed site of the twin giants becomes an issue of concern for architect Cesar Pelli.
You need to go down to bedrock, and you had to go very deep to start finding limestone. And the limestone that we found was like Swiss cheese.
This fissured limestone requires drilling the building's foundation piles extraordinarily deep, over 400 feet underground, or more than 6 times the depth needed to build the JR Central Towers. Once the foundation piles are in, over 70,000 tons of concrete are cast into the mat slab. Pouring round the clock, the work continues for 3 straight days.
This was the largest single pour of concrete ever done.
Timing and precision of the pour must be perfect. If one side of the foundation were to dry and settle before the entire job is completed, an uneven base would result. If the skyscraper were built on an uneven base, the building's weight distribution would be uneven. Out of balance, an earthquake could easily bring it tumbling down. But will these enormous mat slab foundations safeguard the buildings during a major earthquake? Or could they still topple to the ground, as in Mexico City and Kobe?
Eventually we'll see an earthquake in a major city that's a very large earthquake, and I think the bad news is that we could see some severe unanticipated damage and perhaps even collapse of some tall buildings.
The JR Central Towers, soon to be Japan's tallest building, is designed to withstand a magnitude 8.0 earthquake. Its engineers believe the skyscraper is safe, built to withstand the types of earthquakes that frequently strike the island nation. A similar faith in building design has guided engineers in Los Angeles for years. And on January 17, 1994, when a magnitude 6.8 earthquake strikes Southern California, their faith is shattered. In some areas, engineering fails and structures crumble. Amazingly, none of LA's skyscrapers collapsed. But an inspection of their inner steel cage frames reveals major damage in the welds connecting the vertical columns of many buildings to their horizontal beams.
The cracks did not only remain in the body of the weld that connected the two pieces. Once it started, it propagated. That crack had the effect like a zipper effect. It went right through the main body of the column element, and it ruptured the column horizontally.
Luckily, the Northridge quake was short, only 20 seconds. Laboratory tests show that had the shaking lasted as long as either Mexico City or Kobe, these cracked beams would have ruptured completely, causing structural failure in many of these buildings. While Los Angeles struggles to repair its damaged skyscrapers, the sobering news has sent shockwave throughout the engineering world. The steel cage structure, once thought safe, is now vulnerable during a strong earthquake.
Engineers of the JR Central Towers and the Petronas Towers must now implement the latest technology to keep their skyscrapers upright. To safeguard the millions of people who use Nagoya Station under the JR Central Towers. And to keep the Petronas Towers as the tallest building in the world. In the aftermath of the Northridge earthquake in Southern California, tall building engineers have answered a troubling question. After years of research, a possible solution exists for the stress-induced failures that many buildings sustain during earthquakes. Skyscrapers all over the world, including the JR Central Towers in Nagoya, now use what's known as dampers. These devices, installed within the diagonal trusses of the steel cage structure, reduce the building's shaking during a quake, much like shock absorbers in a car.
If you put a brace diagonally across it, as you deform the frame, that element would shorten and lengthen. And so if in that brace you actually put a damper, some sort of hydraulic valve, then it would absorb energy as it lengthened and shortened.
A skyscraper with dampers can absorb up to 3 times more energy produced by an earthquake than a building without them. The longer a quake lasts, the more effective a damper can be, absorbing more energy with each shock wave. Tall building engineers have been quick to adopt the damper technology. 14 have been installed within Petronas Twin Towers, and 6 are being installed in the JR Central Towers. While engineers in Nagoya and Kuala Lumpur incorporate technology to combat potentially destructive earthquakes, another, more immediate danger swirls above. The wind affects all skyscrapers. The taller a building rises, the stronger the wind it faces. Skyscraper design must take into account these turbulent forces. Towering over 1,400 feet above Chicago, the Sears Tower sustains daily gusts that can average 75 miles per hour.
The wind force, by and large, dominates these very tall buildings, dominates the design. It's more important than the weight of the building in the sense of just holding it up. It is the dominant force. The wind is what drives the design of very tall buildings.
When wind hits a building, it acts much like the sail of a boat. In order to withstand these blustery forces, a tall building must be flexible enough to bend and absorb some of the wind, while still remaining rigid enough not to topple over, or even snap in half. The JR Central Towers provides a model of how this balance is achieved. The 3 inner steel cages provide flexibility, allowing the towers to sway up to 4.5 feet in strong winds, while the rigid central core of reinforced concrete adds the stability needed to prevent the tower from snapping in winds gusting up to 175 miles per hour. However, as skyscrapers are built higher and higher, they encounter stronger winds and are required to sway even farther to remain upright. Architects must now deal with a whole new design problem.
It's going to wobble like a tuning fork in order to maintain its structural integrity under those forces. So the question now is a more difficult one. It's not artistic, it's not properly scientific, it's judgmental, and it's about human comfort. It's about, on those top floors, how much vibration can people in offices tolerate and be comfortable with? At what point do we need someone at the elevator vestibule at the top handing out Dramamine?
If a swaying skyscraper can cause motion sickness in average high wind conditions, then the occupants of the Petronas Towers had better prepare for a wild ride.
Reaching nearly 1,500 feet, the Twin Towers are designed to withstand the devastating winds that strike the region.
These swirling gusts can reach over 90 miles per hour. Already, the world record height of these towers has pushed modern technology to its limits. Each tower needs to sway almost 3 feet just to prevent a structural collapse.
Yeah, it's a little bit small.
But architect Cesar Pelli has a vision that will compound this problem. A bridge between the 2 towers, a structure that Pelli feels will be symbolic of something larger than the towers themselves, the human spirit.
We proposed the bridge connecting the 2 towers in the 40th and 41st floors. And the bridge with its supports marks a gate also to the sky.
Pelli's architectural vision clashed with the tower's physical reality. If each tower must sway independently, how can it do so while attached to the bridge? The realization of this dream will stretch both Pelli's and the engineer's skills to their limits. It takes over 30 hours for construction crews to lift the sky bridge into position. But the real danger exists after the 900-ton passageway is locked in place. What would happen if the swirling winds hit the twin towers from different angles simultaneously, and they swayed in different directions? The answer is frighteningly simple. The bridge will snap apart, plummeting over 600 feet onto a crowded walkway below. To solve this unique design problem, engineers borrowed something from earthquake technology: dampers. Critical to the sky bridge's design are its two spherical support legs, 117 feet long and weighing 60 tons each.
In essence, these two legs are enormous dampers that will help absorb the vibrations created when both buildings sway.
To prevent these legs from snapping off when each tower sways in opposite directions, a torque reduction system is used. Instead of anchoring them to the bridge and towers directly, the support legs are attached to a rotating plate that can twist at least 45 degrees in any direction. The result? The damper legs absorb the torque and sway, while the bridge's interior support system remains unaffected. After the towers open, the bridge will serve not only as a passageway between the two towers, but also as an escape route in case of fires or emergencies. This combination of artistic design and engineering technology allows Pelli to realize his architectural dream.
When I face that space between the towers, I am in direct contact with the sky, with a higher world.
Pelli was able to implement his design for the Petronas Towers. Sometimes the forces that can upset plans come from the most unexpected places. In Japan, where cable television hasn't taken root, most television signals are broadcast through the air. The JR Central Towers, as they're being built today, are round. In the original plan, they were square. However, it became clear that a rectangular tower 800 feet in the air would block transmission signals from local TV stations. The result would be a phenomenon known as TV ghosting.
TV ghosting is a very common phenomenon. If you're looking at your television set and you get two images that blur your reception, that's called TV ghosting.
The architects of the JR Central Towers were surprised by this structural problem and forced to make a multi-million-dollar design change or suffer the wrath of thousands of television viewers.
Those curves, from an aesthetic point of view, they were very nice, but also from a technical point, what it does is it takes a direct wave and then diverts it.
For a building to divert a broadcast wave, the exterior can't contain any metal or reflective glass that would cause the wave to bounce back toward the transmission tower. So the exterior of the JR Central Towers had to be made of precast concrete and ceramic tile, a much heavier skin than the glass covering originally planned. This extra weight on the frame of the skyscraper made it even more necessary to place a massive mat slab foundation underneath the building. In the end, the architects and engineers for both the JR Central Towers and the Petronas Towers are able to fulfill their visions. The 800-foot JR Central Towers will become the tallest building in Japan, providing desperately needed office and retail space to a growing metropolis. And the Petronas Tower will win the title, tallest building in the world. But have these engineers, while building such enormous skyscrapers, prepared for every disaster? Or is it impossible for an architect to prepare for the insanity of man? Designed to survive the battering of high winds and the violent shaking of earthquakes, modern skyscrapers seem indestructible. But where Mother Nature might fail, man has succeeded. On February 26, 1993, a nightmare becomes a reality. The bombing of New York's World Trade Center ushers in a dark new reality. The threat of terrorism has finally come home. The blast kills 6 people, injures over 1,000, and causes millions of dollars worth of damage. But as enormous as the force of the explosion is, it doesn't bring down the towers or even cause severe damage to the structure of the building.
You must understand that the towers were designed for the impacting of the largest airplane of its time, the Intercontinental 707 aircraft, right into the building.
In designing the World Trade Towers to withstand a mid-air collision, engineers learned after the bombing that they had inadvertently built a fire trap.
Both towers actually behaved like giant chimneys, and they took this air that was in this basement created by this great explosion and sucked it up into the towers and raised it up through and tried to expel it at the top.
Somewhere among 110 stories, 50,000 people are stranded in complete darkness. When emergency systems fail, smoke fills the towers and people become desperate for air. They smash windows in a frantic search for a way out. Yet they're alive because the tower didn't collapse. The steel cage skeleton absorbed the force of the bomb and prevented its collapse by distributing the blast shock throughout the entire frame. However, the inner concrete reinforced columns, designed to give the towers their rigidity, became the vertical conduits for the deadly fire and smoke. Eventually, firefighters were able to release the trapped smoke by smashing windows on the lower floors and cutting air holes in the roof of the towers. During the ensuing investigation, engineers discovered the structural design of the World Trade Center can survive a bomb's blast, but the building's emergency fire and sprinkler systems can't. They were knocked offline, allowing the spread of the fire and smoke. Since the current steel cage structure is essential to building a skyscraper, architects can't change this design component. Yet disasters like the World Trade bombing and the MGM hotel fire of 1977 can turn skyscrapers into towering infernos. Engineers are now challenged with developing an advanced infrastructure to ensure that the air, water, and fire systems can function under extreme situations. Once again, as architects continue to design skyscrapers higher and higher, engineers struggle to invent new systems to support these record heights. For the engineers of the Petronas Towers, simply providing water to the entire building becomes their biggest obstacle. Over 600 pounds of pressure will be needed to pump water to the pinnacle of this skyscraper, nearly 1,500 feet into the sky. Simply attaching a faucet or sprinkler to such highly pressurized water would be like trying to drink from the end of a firefighter's hose. To solve this problem, engineers decide to pump water to the very top of the building and then let it cascade down to pumps located in the maintenance floors below, losing its pressure as it trickles down. At each floor, the water is then distributed throughout the tower. In order to achieve this, 3 entire floors within each tower are dedicated solely to maintenance systems. Located at the 7th, 43rd, and 81st floors, these control areas handle the water, air, and electrical distribution for the floors attached to their zone. If during a fire or explosion one of these maintenance floors is destroyed, the other 2 can operate independently to suppress any fire and ventilate any smoke. During the World Trade Center bombing, once the main control area was knocked offline by the blast, all emergency systems throughout the skyscraper were lost. The 3 independent control areas in the Petronas Towers are designed to avoid just such a fate. This decentralized plan provides a reliable means to a more comfortable environment for the tenants.
You know, you take it for granted that you're cool, you're warm, there's lights on, the bathrooms work, and there's some very, very sophisticated systems in your building, particularly today.
These high-tech solutions to old problems have made possible the continued growth of modern skyscrapers. But this technology doesn't come cheap. In Nagoya, Japan, it will take 7 years to complete the JR Central Towers. And it's costing $1 million a day to build this skyscraper. But for all the money that's spent, it's the skill of the high steel worker that makes all skyscrapers possible. In Japan, the people who work on these tall buildings are some of the most talented and dedicated workers in the world. At the JR Central Towers, the project is viewed as a team job. Each morning, workers perform calisthenics together. A detailed briefing of precisely what work needs to be completed that day follows. The coordination between departments is so precise that the day's work is planned down to the minute.
The skill of the worker in Japan is at a very high level. They devote their lives to the construction industry.
This dedication has paid off for the JR Central Towers. Construction is on schedule and under budget, with workers completing an astonishing 3 floors per week. Elsewhere around the world, the completion of 1 floor per week is acceptable. But for the many workers on the high steel in Nagoya, being average is not acceptable, and their passion is spreading. Japanese engineers and workers often train crews building skyscrapers along the Pacific Rim. They came to Kuala Lumpur, and the results stand before all the world to see. Highly skilled workers, technological advances, the dreams of architects. These are the ingredients to build the modern skyscraper. It's guided engineers to build the JR Central Towers 800 feet above a crowded metropolis in the heart of earthquake country. And it's inspired Cesar Pelli to design and erect the tallest building in the world as a monument to a proud city. But in this race to reach new and unimaginable heights, how high is high enough? The drive to create the tallest skyscraper in the world has been a 100-year odyssey sweeping engineers and architects far beyond their initial dreams. This ambitious race has led Cesar Pelli and the engineers of the Petronas Towers to the forefront of modern building design. The $800 million invested by their builders have made the Petronas Towers the tallest building in the world. Their 88 floors soar 1,483 feet into the air. Or is it? Engineers of the Sears Tower say their building still retains the title, since it has 110 floors to Petronas' 88. But Pelli's building includes an enormous spire that tops the building off 22 feet higher than the Chicago skyscraper. Sears Towers officials counter that if Petronas' spire is counted, then the antennas on their skyscraper should be counted too, which raise its height 231 feet taller than the Malaysian giant. Pelli argues that his spire is integral to the design of Petronas, and the Sears antenna are just that, antennas. But if the height to the tallest antenna is the standard, then isn't New York's World Trade Center the tallest building in the world at 1,758 feet? This debate will become more intense very soon, because in Shanghai, ground has broken on the Mori Towers project. When finished, it will loom over this ancient Chinese city at a height of 1,509 feet, taller than both Sears and Petronas. In Hong Kong, Manila, and Tokyo, the city skylines are punctuated with buildings under construction. Is this where the next Petronas will rise? The key to taller skyscrapers is once again the elevator.
We took a 145-story building, put all the elevators in it that were needed by all the people in 3 million square feet that were to occupy that building. The entire floor plate would be taken up by the elevator core and there'd be no space to rent and make money on. So, hey, that wouldn't work, right?
Recently, the Otis Company announced its latest creation, which many believe will solve this dilemma. An elevator that can move horizontally as well as vertically. By providing access to more areas of a skyscraper with fewer elevators, valuable rental space is opened up. Once a building becomes economically viable to investors, how long will it take before a higher one is built? And how long before another technological advancement comes along that raises tall buildings to unheard of heights? In Metropolis, filmmaker Fritz Lang's prophesizing drama of 1928, even the sky isn't insurmountable. But is there a physical boundary beyond which science can never advance? Years ago, a mile-high building with atomic-powered elevators connecting over 528 floors was designed by American architect Frank Lloyd Wright. If built, a skyscraper this tall would stand over 5 times the height of today's tallest structures. 40 years ago, a mile-high building seemed a futuristic folly. But is it still? As technology continues to advance, engineers now say a mile-high building is possible. New, lighter building materials are the key. Already, ceramics are being used in the exterior walls of the JR Central Towers to lighten the total weight of the building and reduce the stress on the earthquake-sensitive foundation.
The future is going to be, you do not limit yourself to natural materials like steel or aluminum or masonry, where you compose materials and you create new properties out of hybrid materials, alloys or ceramics or plastics, carbon fibers, or mixes of all this.
Eventually, these new materials will give rise to skyscrapers taller than anyone has ever seen, surpassing both the JR Central Towers and the Petronas Towers, today's architectural marvels. These monoliths of the future may also be closer to Lang's vision of the future. Not just a tower of office space, but self-contained cities within a building.
Everything is in one building. You can have retail, you can have hotel, office, apartments, and you can have transportation, all in one single building. You can go to one location and get everything you want.
Since their earliest beginnings, skyscrapers have evoked unexplainable emotions in us, from pride to awe to fear. Have they evolved to become buildings that provide the space needed for a growing population, or just an exploitation of those needs? A justification to build what Cesar Pelli calls a gateway to the skies.
I do not know if it's innate in human beings or acquire culturally. But there is something magic and extraordinary on a structure that grows from the ground and moves up and reaches the sky. When you are up on a building, you and the ground are one. Somehow you feel that through your body, through your feet, through the structure of the building, you are still rooted on the ground, but you are looking above all other buildings. And there is just something extraordinarily satisfying. I imagine the tallest oak in a forest or the tallest sequoia must feel the same thing.
Perhaps these monuments that we leave behind tell much of the human story itself. They speak with stunning eloquence of our ambition and our brilliance, but also of our frailty. As they puncture the skies above our urban landscape, skyscrapers also punch holes in our preconception of what's possible. What was impossible yesterday now stands before us.